Summarizing the previous video presentations in this series on managing small batch manufacturing, let me highlight a couple of the most important points. First of all, production management is not planning, or more precisely, not only planning. It is a set of interrelated business processes, including organization, planning, dispatching, and performance monitoring, assuming reliable feedback and appropriate early warning indicators. As for the organization, the logistic structure of the system is not given to us from above. We create it ourselves. It can be an A-type plant or V-type plant, or some other simpler or more complicated logistics. And if someone claims, let's say, that his management tools do not depend on the system's structure, or, moreover, that the main problem is to develop the best production schedule, but everything else is not his business, then this should rather be considered bad news. The second point is that production planning does not necessarily mean operations detailed scheduling. For instance, there is no such planning in the Toyota production system. In particular, they don't set up in advance the start and completion dates for each individual operation. To distinguish the TPS planning mode, I will call this sequencing instead of scheduling. The third point is that in a small batch manufacturing, due to its characteristic high variability, strong dependency, and non-linearity, the execution times become unpredictable, an order of magnitude exceeding the corresponding total processing times. And therefore, a Taylor-type management model based on operations detailed scheduling is not applicable, not to mention the suboptimality and structural instability of the resulting mathematical solutions. On the other hand, in order for any system to be manageable, the following necessary conditions must be met. A single command post providing coordinated control actions. The magnitude of the control actions themselves must exceed the internal noise level. If, for example, variations in production lead times are measured in days, planning in hours doesn't make sense then. An explicit stabilization mechanism should be implemented. Otherwise, you will never know whether the change in the production state is due to your control actions or just because of the system's instability. Finally, it was proposed to develop a new management model, an alternative to the Taylor-type one, suitable for a small batch operating environment, and based on appropriately modified key logistics components of the Toyota production system. Within this Toyota-type management model, operations detailed scheduling should be replaced by sequence planning, taking uncertainty buffering into account. And the emphasis in execution should be shifted from trying to follow preliminary created detailed time schedules to dispatching work in process based on current time-varying priorities. Without going into technical details, I will briefly describe now how these 5 key TPS components can be adopted for small batch manufacturing with an A-type or similar logistics structure. As for the pacemaker process, the situation looks pretty simple. In Toyota, this is the main or assembly line, where the last processing step is performed. Obviously, if you need a single command post to control all production, the best choice would definitely be the step through which all material flows pass. Therefore, the appointment of an assembly as a pacemaker process will be quite reasonable for any A-type plant, where the parts manufacturing and assembly production units are separated by a kitting point. Note that in the theory of constraints, such an element is sometimes referred to as a strategic constraint of the entire system. This approach should ensure, on the one hand, the consistency of the master production schedule with the sales or finished goods shipment plan, the so-called external synchronization, and on the other hand, smoothing out the manifestations of the bullwhip effect and overloading of the capacity-constrained resources in the assembly feeding channels, the so-called internal synchronization. To this end, for the mixed model cases, the only detailed instruction sheet is developed in Toyota on a daily basis, in the form of a sequence of car models introduced into the main line, so-called Heijunka sequence and leveling plan, calculated in accordance with a quite sophisticated algorithm, as mentioned in one of the previous video presentations of this series. An integer, nonlinear NP-hard optimization problem is solved in Toyota for this purpose, whereas the corresponding technique that is believed the TPS cornerstone is proprietary and is considered a black box. In our situation, depending on the logistic structure of the system, as well as the completeness and reliability of the initial data, similar approaches can be used to level production. In general, this requires additional built-in buffer protection in each of the feeding channels. But in some particular cases, due to the specially developed flow synchronization tools, it is quite possible to significantly reduce the size of such buffers, and consequently the production lead time. For example, in this simple but real case with 4 end products and a given shipment plan, Heijunka type leveling can be performed according to the shown master production schedule, obtained by determining some mixture of items to be manufactured in each of the 12 sequential time intervals. Unlike Toyota, where only one assembly unit is released during attack time, a mixed aggregated plan is formed for a small batch production. As for the pooling technique, the priorities of replenishing the mainline posts with the necessary components in Toyota are determined by the dynamics of their actual more or less even consumption. Production lead times are usually short, and the first-come, first-served policy is quite effective. So the classic Kanban is perfect for such a production environment. In small batch manufacturing, however, consumption rates can vary significantly over time, even if you produce some parts to stock. Therefore, it would be pretty wise to be able to change the release and processing sequences accordingly. An appropriate technique developed within the theory of constraints and called MTA was briefly described in the previous video presentation of this series. It is very similar to Kanban, but is more flexible in a highly uncertain operating environment. In particular, the priority of each formed replenishment production order changes dynamically in time depending on the current manufacturing state. Another important feature of small batch operating environment is the wide range of products, where many, if not all, finished goods are made according to customer orders. This usually means shipping as well as manufacturing the relevant parts and components to specified due dates and in certain quantities. The general idea of the corresponding SDBR logistics solution, developed within the theory of constraints, was also briefly described in the previous video presentation of this series. To explain this mechanism in more detail, let's assume that 3 different parts need to be manufactured by some assembly start date, instead of senseless manipulations with the standard operation times. A so-called production lead time buffer is introduced for each part. That is, a time interval sufficient for this part to pass through all manufacturing steps with a stably loaded system. As a result of such rough planning, preliminary start dates for the execution of the relevant production orders are determined. And as part of this solution, the priority of each production order at any given time is calculated as the degree of penetration into the corresponding time buffer. For example, in the diagram shown at the current date, the priority of the third production order is 50%, yellow zone. The second is 67%, on the border of the yellow and red zones, and the first is 80%, red zone. Some may claim that it is very difficult to set time buffers for hundreds and thousands of parts, subassemblies, and assembly units in production. I note once again that in the variations world we are not talking about precise numbers, and if the actual variability is measured in days, there is no point in planning anything in hours, let alone minutes. In addition, there are fairly simple practical approaches for assigning time buffers. Anyway, the stability of the production system is much more important. As is well known from the factory physics fundamentals, a prerequisite for the stable operation of any production system is that releases are regulated in a manner preventing work in process from growing beyond a specified limit or WIP cap. In TPS, this is done in the simplest way by fixing the number of Kanbans at each processing step. In our situation, when Kanban is not applied, the necessary explicit mechanism can control the work in process level in each production line, or in groups of lines, or in the entire system at once. In such a case, thanks to the principle of an optimal operating mode existence, briefly described in one of the previous video presentations of this series, it becomes possible to fully control manufacturing and to make the system really pull. The last but not least TPS key component is visualization. In this regard, in Toyota they usually talk about Kanban cards, Heijunka boxes, and all kinds of the shop floor dashboards. Meanwhile, in a high uncertainty operating environment, typical for small batch manufacturing, such a function is of particular importance, especially when the emphasis shifts from detailed planning to dispatching. We badly need a special tool that allows us to identify troubles foreseen in the future, sort of the terrain awareness and warning system in modern aviation. Within the framework of the proposed management model and the corresponding information model, which will be briefly described in the third part of this series of video presentations, the so-called production state diagram may be a suitable option. The fact is that with our approach, every production order, whether make to stock or to order, at any given time has two major attributes, priority and readiness, which dynamically change from 0 to 100% each. And we believe that the task is performed normally if its readiness approximately corresponds to its priority. In other words, if the point on the plane is located close to the diagonal. So if dozens, hundreds, or even thousands of tasks are in production at the same time, it becomes easy to understand what should be paid special attention to and what does not require management intervention. In particular, the field near the diagonal is supposed to be normal operation area. Tasks falling into a high-risk zone with high priority and low readiness require special attention and perhaps some urgent managerial decisions. So as those tasks with low priority and high readiness. For the convenience of visual analysis, two additional sectors can be introduced: close attention area and ahead execution zone, along with an appropriate coloring. The resultant picture may look like this, that makes it possible to observe the whole manufacturing at one glance.